Hello, this lecture is an introduction to solving intractable problems. We'll start by discussing what are these intractable problems. So we call them NP-hard problems, and what can you do when we face such a problem. And we'll zoom in on two specific kinds of algorithms that we can design for such NP-hard problems, exponential time algorithms and parameterized algorithms. So one of the central questions of computer science is P versus NP. So the question whether adding non-determinism adds some computational power. So P is the class of problems that can be solved in polynomial time. NP is the set of problems that can be solved in polynomial time by a non-deterministic Turing machine. So Turing machines that are able to guess solutions and then check whether these solutions are correct all in polynomial time. So this guessing part is basically where the machine transitions into many possible worlds, and then for each of these worlds it can then check in polynomial time whether the desired solution has been found. So it is believed that P is different from NP, and therefore that there are problems in NP that cannot be solved in polynomial time. So this guessing stage, if we wanted to design a deterministic algorithm for this guessing stage, this would necessarily take exponential time. But we don't know if this is true. This hasn't been proven, but there's a strong belief that NP-hard problems cannot be solved in polynomial time. So the NP-hard problems are at least as hard as any other problem or as any problem in NP. And currently we don't know any polynomial time algorithm for any such NP-hard problem. Also, if you would find a polynomial time algorithm for one NP-hard problem, then all problems in NP could then be solved in polynomial time. So it's a big hurdle to be able to solve an NP-hard problem in polynomial time. Nobody has managed to do it so far. So what else can we do? Should we just give up, or can we use other approaches to tackle these problems? Let me give you an example. So it's a situation of a power grid manager. So Tammy is responsible for fault detection on the power grid of an energy company. She has access to K monitoring devices. Each one can be placed on a node of the electrical grid and can monitor the power lines that are connected to this node. So one monitoring station gets put on a node and it monitors all the edges or the lines that are connected to this node. Now Tammy has only K such monitoring devices, and her objective is to place them onto nodes such that every power line in the network, in this grid, in this electrical grid, is monitored. So the grid might be very large, but she only has K such monitoring devices. She cannot afford to put one on every node of the power grid. So she needs to be strategic in placing these so that every power line can be monitored. And so if we have a power line, let's say it connects two nodes, then it's sufficient that at least one of these endpoints of the power line contains a monitoring device. So let us first give an abstraction of this problem. So we have a problem on the power grid with some specific monitoring devices, but actually what really matters is, well, this network, and the fact that selecting a node where we put such a monitoring device basically covers all the edges that are connected to this node. So in terms of graph theory, we get the vertex cover problem. So what's a vertex cover of a graph? Well, it's a subset of vertices such that every edge in the graph has an endpoint in this subset. So we need to select vertices that cover all the edges of the graph. Okay. So in the vertex cover problem, that's a decision problem. So the input is a graph G and an integer K. And the question is, does G have a vertex cover of size K? So is it possible to place these K monitoring devices onto nodes of the power grid such that every single edge of the power grid is monitored? Well, this is a decision problem. What Tammy actually wants is to find the actual placement of the monitoring devices. But of course, if you can find the actual placement, then you can also solve the decision problem. It's not completely clear that if you can solve the decision problem, then you can also find the placement. But there's a kind of self-reduction that actually enables you to do this. Okay. So the decision problem and the actual placement problem are very closely related. And vertex cover is one of these NP-complete problems. So NP-complete means that it is in NP and it's also NP hard. There are much more details on NP hardness and NP completeness in the lecture on this topic. Okay, so in this example graph here, the red vertices, they cover all the edges of the graph. So if we have this graph and k equals 4 as an input, then this is a yes instance. Because there is actually such a vertex cover that covers all the edges. So in terms of this non-determinism, so a non-deterministic algorithm that runs in polynomial time would first of all guess 4 vertices of the graph. And then it checks in polynomial time whether this selection of 4 vertices is actually a vertex cover of the graph. Right? And checking whether a set of vertices is a vertex cover of a graph, that can be done in polynomial time. So we just need to tick off each edge and check whether one of the endpoints is selected. Okay, but this problem is NP complete. So, and normal computers don't have access to non-determinism. If we want to guess something, we have to try all possibilities of these guesses, right? A non-deterministic machine can do these guesses all in parallel. Okay, so what can we do if we're facing such an NP-complete problem, specifically for this vertex cover problem? Well, there's several approaches. So one well-known approach is design approximation algorithms. So this means that we design an algorithm that doesn't actually solve the problem. So it doesn't actually solve this problem, but it solves something close to this. So this is a decision problem. We can also discuss the corresponding optimization problem, which is what is the smallest k such that this graph has a vertex cover of size k. Okay, so let's say the smallest such k is opt, so we call it opt. It's the size of the smallest vertex cover of G. And now an approximation algorithm would give us a vertex cover of size at most 2 times opt. So basically, if it's possible to cover all the edges of the graph with k vertices, then this approximation algorithm would give us 2k vertices that would cover together all the edges of the graph. We could try and find an exact algorithm, so in contrast to the approximation algorithm, so that actually finds a placement or a selection of k vertices that together cover all the edges of the graph, if it's possible. But So we already discussed that nobody knows how to do this in polynomial time, but we can design an exponential time algorithm that's faster than brute force. So we don't want to try all the vertex subsets or all the size 4 vertex subsets. We can still try and use an exponential time algorithm, but that's much faster than brute force. So and for vertex cover, there is actually an algorithm that runs in time 1.1970 to the n. So that's exponential, but it's moderately exponential. There's also fixed parameter algorithms. So here we still have an exponential running time, as you see here. It's 1.2738 to the power k plus something polynomial. But so notice that the exponential part only depends on k. So if we just look at the exponential part, the size of the instance doesn't appear. I forgot to mention n is of course the number of vertices of the graph. If we are not happy with exponential running times, even moderately exponential running times or exponential running times that depend on a parameter that's smaller than the number of vertices, then we can also design heuristics. So those are quite similar to approximation algorithms, but they don't give us a guarantee of optimality. Like for the approximation algorithm up here, we had a true approximation algorithm because it gave us a vertex cover of size at most twice the size of the smallest vertex cover. For heuristics, we typically don't have such guarantees, but then people show that in practice, they actually work well. So in practice, they often find small vertex covers on the selection of benchmark instances, but one usually speaks of a heuristic when we don't know an approximation guarantee. The other thing we can do is maybe our application has only very specific instances. So let's say the power grid might be a bipartite graph. So we might not have any odd cycles in our graph. And then sometimes if we have restrictions on the input, like the graph might be a tree or an interval graph or one of these other special graphs from special graph classes, then sometimes we can exploit these properties that these graph classes have and actually design polynomial time algorithms. We could also think about quantum algorithms. So if someday we get access to quantum computers, can quantum algorithms actually help? It's not believed that they can solve NP-hard problems in polynomial time, actually. They might be able to speed up like algorithms, like exact exponential time algorithms, but not down to a polynomial running time. They might still help. Okay, so in this course, we are discussing the design and analysis of algorithms for NP-hard problems. Our main focus is algorithms that solve these NP-hard problems exactly, and then we analyze their worst case running time. We will also briefly touch on approximation algorithms, where we get a guarantee of the optimality, but we always only look at the worst case running time. So we don't do average case analysis or typical case analysis, which are much more difficult to do, actually. Let's start with exponential time algorithms. And let's first make clear what do we mean by exponential time, because we need to somehow make the difference between doubly exponential time, exponential, sub-exponential time, etc. So first, let's start with polynomial time. So those are algorithms that we know and love, so our polynomial time algorithms. And those are algorithms that run in time order n to the power c for some constant c. So this also includes running times such as n log n, because we can upper bound those running times by a polynomial as well. If we don't really care about what the particular constant c is, we can just write n to the power order 1, or equivalently poly n. Then there's the quasi-polynomial time algorithms. So here we have running times of the form 2 to the order log n to the power c. So and these typically arise when we have running times like n to the power log n. So we might have, let's say, a set of size n, and we need to select log n elements of this set. And there's n to the power log n possibilities of doing this, and now we might run a polynomial time check for each of them. So then we end up with running times that are of this form. Notice that n is equal to 2 to the power log n. So in total, so this would be 2 to the power log n squared, which is the same as log 2n. Okay, so this is where such running times come into play, and n to the power log n is of course larger than n to the power c. And 2 to the power log n squared is also smaller than, or it goes slower than 2 to the power of a polynomial in n. Then we have the sub-exponential time algorithms. So those have a running time that's of the form 2 to the little o of n. So little o of n is any function that grows asymptotically strictly slower than linear. So an example of a function that grows strictly slower than linear is square root of n, for example. So here we have running times that look like 2 to the square root of n times log n, or something like this. And then we have the exponential time running times, which is 2 to the power poly n. So it could be 2 to the power 0.2 times n. It could be 2 to the power n. It could be 2 to the power n squared. So that's also still exponential time. And then for doubly exponential time algorithms, those have running times of the form 2 to the poly n. So we have in the exponent, we have another exponential function. Okay, and then oftentimes when we write out the running time of an algorithm, specifically if we have an exponential time algorithm, then we often want to ignore the polynomial factors because they grow asymptotically much slower than the exponential part. So we want to focus on the exponential part of the running time, and there we have this O star notation, which ignores polynomial factors in the input size. So if we have a running time that's order 2 to the n times n squared, we can just use the O star notation to say that this is O star of 2 to the power n. Okay. It turns out that every problem in NP can be solved in exponential time. So we'll see the details in the lecture on NP completeness. Roughly, this is because, well, this guessing step can be simulated in exponential time. We don't need doubly exponential time is enough. Let's see a few examples of NP-complete problems. So there's lots of NP-complete problems that fit into these three categories. We have the set of subset problems, and then we have permutation problems and partition problems. And so these always tell us how this guessing stage looks like. So like in a subset problem, the non-deterministic Turing machine would guess a subset of something and then do a polynomial time check. In a permutation problem, it would guess a permutation of something, and in a partition problem, it would partition a set. Our representative of a subset problem is independent set. So an independent set in a graph is a subset of vertices that contains pairwise non-adjacent vertices. So it's a set of vertices such that there's no edge joining any two vertices in this set. And in the independent set problem, in this decision problem, the input is a graph G and an integer k. And the question is whether G has an independent set of size k. So can we select k vertices of the graph such that there's no edge that joins any two selected vertices? And if we want to think about the simplest brute force algorithm we could imagine, so as brute force, we view this as the simplest possible guess and check algorithm. So what do we need to guess? Well, we need to guess a subset of vertices. And what do we need to check? Well, we need to check two things. One is whether this subset of vertices has size k. And the second thing is whether there's no edge joining any two selected vertices. And the checking part can be done in polynomial time. But how much time does the guessing part take? So if we want to guess a subset of vertices, or if we want to go through all subsets of vertices, how many are there? Well, for every single vertex, we have two possibilities. Either we put it in the set, or we don't. So if n is our number of vertices, we get a total of 2 to the power n possibilities for the number of subsets of vertices. Because for every vertex, for every one of the n vertices, we have two possibilities. Right? So, and since the checking part can be done in polynomial time, in total, we get a brute force algorithm whose running time is O star of 2 to the power n. So, and this works not just for independent set, but for all subset problems where the ground set of the things that we need to select has size n. So if we have a subset problem, we can always solve it in 2 to the n time. And the difficulty is often to do faster than this brute force 2 to the n running time. As a representative of a permutation problem, we have the traveling salesperson problem, or TSP. So the input is a set of n cities. We also have the distance between every two cities in the input, and we have an integer k in the input. And the question is whether there's a tour, so a permutation of the cities, such that the total distance when the salesperson travels from one city to the next, according to this permutation, so the total distance traveled must be at most k. So the question is whether this is possible to find a tour with total distance at most k. So if somebody gives us a tour, so permutation of cities, of all the cities, so we need to visit everybody, all the cities, and then we need to return back to our original city. So if somebody gives us such a tour, then, well, it's easy to add up the distances. So we can easily check in polynomial time whether the size of or the length of this tour is at most k. So the computationally intensive part is the guessing of this tour, or the enumeration of all possible permutations of cities. And of course we have, like if we have n cities, we have n possibilities of selecting the first city, then n minus 1 remaining possibilities of selecting the second city, n minus 2 for the third city, and so on. So in total, we get an n factorial warning time. So what is n factorial? If you want to translate this into something that's either exponential or sub-exponential and so on, well, we can use Stirling's approximation, where, well, in the O star notation, this would be an n to the power n running time, and this is of course 2 to the order n log n, because again we can replace the n here in the base by 2 to the power log n, and then we also have an n in the exponent. Okay, so this is a bit slower than what we had for subset problems, because, well, we have this additional factor here in the running time, in the exponent of the running time. As an example of a partition problem, we have graph coloring. So what is graph coloring? So a k-coloring of a graph is a function that assigns colors or integers from 1 to k to the set of vertices, such that no two adjacent vertices receive the same color. So if we have two adjacent vertices, they cannot get the same color, and now a k-coloring is such a coloring that uses only k colors, so integers from 1 to k. So in the coloring problem, the input is a graph G and an integer k, and the question is whether G has a k coloring. So is it possible to use k colors to color all the vertices of the graph, such that no two adjacent vertices have the same color? So in particular, every color class needs to be an independent set. So this means that now the question is whether we can partition the vertex set of the graph into k independent sets. So this gives us a partitioning problem, and how many ways are there to partition the vertex set of a graph? So this is, so if we fix the number of colors k, then there's k to the power n possibilities. So for each one of the n vertices, we can put it into one of k buckets. And the buckets are our color classes. Alternatively, we can view it as for each of the n vertices, we have k possibilities of assigning a color to that vertex. So we get a running time that's O star of k to the power n. So there are instances where we don't know what the number of parts of the partitions is, and then we get something, a running time proportional to the Bell number, and so the Bell number is 2 to the order n log n, same as for permutations. Okay, so why would we care about exponential time algorithms? Well, first of all, it's a very natural question in algorithms. Like, we're given a problem, how fast can we solve it? What's the best running time we can obtain? Do we have to use brute force, or can we do something faster? So, and of course we are interested in the worst case analysis, and we want to design algorithms and prove that their worst case running times are as small as possible. So this might lead to practical algorithms, so for small instances, and it can also lead to efficient subroutines for other algorithms. Like if we have an approximation algorithm that first somehow divides up the graph and then wants to solve each part exactly, then we get some nice approximation algorithms. They might still have exponential time or sub-exponential time, or even polynomial time sometimes. We also can get randomized algorithms with expected polynomial time running times using exponential time algorithms as subroutines again. And then, so oftentimes, if we have a problem, if we're given a problem that's really crucial for some application, you wouldn't just design one algorithm and hope that this is the best algorithm for all possible instances that we could encounter, right? We would design several algorithms or implement several algorithms, and then depending on what kind of instance we get, we then choose, well, a selection of algorithms that we could run on this instance. So in particular, if we happen to get a small instance, we might want to run the exponential time algorithm. If you get a really large instance, we might try and run the heuristic and then maybe also an approximation algorithm, and then return the best solution we got. So the design of exponential time algorithms is one component in solving NP-hard problems. So we have seen that if you want to exactly solve an NP-hard problem, so we can do exhaustive search, which is a trivial brute force method. So for subset problems, we get 2 to the n running times. For permutation problems, we get n factorial running times. And for partition problems, we get running times of the order k to the power n or c to the power n log n. And they all work by trying or guessing all candidate solutions, or so-called certificates, for a ground set of n elements, and then checking in polynomial time whether this is actually a viable certificate. So we have this exhaustive search method, but then oftentimes we can design faster exact algorithms. Not for all problems. For some problems, the best we know is this brute force approach. But for many other problems, it is possible to obtain provably faster worst-case running times. And so the running times are listed here. Those are from the literature. And so the first one is an algorithm for vertex cover on graphs with maximum degree at most 3. The second running time is an algorithm for dominating set. And the last running time is for feedback vertex set on directed graphs, which barely is faster than the 2 to the n brute force algorithm. But the point of that paper was just to show that it is possible to improve on the brute force algorithm. Okay, so what does it mean in practice? So can we actually solve instances of a certain size within a reasonable amount of time? So what I did here is that, so I took a processor that executes 2 to the 38 instructions per second, more or less. And then I checked, okay, so what size of instances can we solve? So if we have an available time of 1 second, so we can execute 2 to the 38 instructions, then here are the running times, or the sizes of the instances that we can solve if this is the running time of our algorithm. So if we have an n to the power 5 time algorithm, we can solve instances up to size 194. If the running time is 2 to the power n, then we can solve instances up to size 38, of course. Because 2 to the 38 equals 2 to the 38. Now, if we have slightly more time, like 1 minute, we can execute more or less 2 to the 44 instructions. If we have an hour, we can execute 2 to the 50 instructions. We probably don't want to run our algorithm for 6 months. The point I wanted to make here is that, well, sometimes, well, if we get really really small exponential running times, like 1.1 to the power n, then we actually can solve quite large instances. Like in a second, we can solve instances up to size 276, which is more than an algorithm that runs in time n to the 5, right? And it is worth trying to improve algorithmic running times, because this actually makes a big difference. Like if we have the 2 to the n algorithm here, like it can solve instances of size up to 38 in a second. If we give it an hour, it still only manages instances of size 50. If instead we design a faster algorithm and get a 1.5 to the n time algorithm, then in a second it can solve instances up to size 65. To solve instances of size 65, the 2 to the n algorithm would need more than 6 months. And that's easily explained by this exponential nature of the running times, right? Okay, so there's a quote by Alan Perlis here, which is the first ever recipient of the Turing Award. He says that for every polynomial time algorithm you have, there is actually an exponential time algorithm that I would rather run. Because well, we can always make these constants here smaller and smaller until the running time of the exponential time algorithm becomes more competitive for all practical instances than the polynomial time algorithm. Okay, so why is it that well, waiting longer or having access to more computational power doesn't make such a big difference as designing faster algorithms? Well, suppose a 2 to the power n algorithm enables us to solve instances up to size x. So if we have a faster processor, like according to Moore's law, processor speed doubles after every 18 to 24 months. So if we wait 18 to 24 months, processing speed has doubled, and now we can solve instances up to size x plus 1. Because 2 to the power x plus 1 is exactly 2 times 2 to the power x. But if instead we design a faster algorithm, for example, one with running time 2 to the n half, then we can suddenly solve instances up to 2 times x. So this multiplicative factor here in the size of the instance we can solve is much more important than the additive factor here that we get from waiting for faster processes.